Yeah, so for your understand, I prepared some just mathematical equation. This is not related to our equilibrium equation. This is a second order difference equation, just second order ordinary difference equation. Yeah, I think that you guys can solve the equation. Maybe this solution maybe express the second order polynomial equation, or yeah, how can you solve it? Maybe that contains those kind of some relationship, and then I think that yeah, this is a homogeneous solution, this is a partial solution, non-homogeneous solution, so that maybe the solution can be expressed looks like this, and then but using our purpose is we obtain the numerical solution, so that yeah, we are going to use a FEM technique in here. So we simply assume that this solution is a first order polynomial equation, and then we use those kind of simple shape function in here. Yeah, maybe n1 is a function of x and n2 is also a function of x. So yeah, you please do not confusing this equation in here, and then you can express the nu and here, and then we are going to use at least two elements in here, so that the shape function is yeah, please using this equation, but generally yeah, we only if you guys can obtain this is a coordination each coordination, so that you can use it. And here, so that after the changing this u is a approximated solution that can be changing the looks like this, and then but our equation is 0, and then I mean that our exact solution, yeah, this solution is always equal to 0, so that residual can be determined, it looks like this. This equation itself can become a residual, and then in previous slide we defined this residual whole domain equal to 0, so that yeah, so that a yeah, remaining things, and then yeah, this part do not yeah, this part separated by in here, and then yeah, v also can be expressed looks like this, or v1 and v2 and n1 and n2, so that, and here we use n2 and n1, and v is in here also. Yeah, this part containing the same part in here, so then yeah, this part yeah, always equal to 0. It is because the shape function is a first order polynomial equation, so that second derivative returns always 0, so that we should apply the integration by part techniques in here. So before we start the integration by part, we can cancel out v1 and v2 does not affect this equation anymore. So, and then this part, yeah, you can take integration by part. Yeah, so this part derivative, this part integrated, and this part where is it? Sorry, derivative, and then integrated, but applied the exact values in here and with a minus here. And then this part, equation, there are no treatment in here. So let's check in here. What is the derivative shape function? In previous slide, maybe you guys already know that maybe they will give those kind of relationship. Maybe, am I right? Sorry, this part minus, this part plus, and then this multiplication is become the 1 over square, 1 minus 1 minus 1 and 1, and then there are no function x function of x, so that you guys can obtain the L in here. So, and then a remaining things, yeah, but in here, yeah, this is a body force, so that yeah, in here there are some variable and x in here, so you should integrate it for the body force. So after the I think that this integration very simple, when 1 over x square and then apply these two variables in here. So the result is looks very looks like this, and then this part, yeah, in here, yeah. So x, yeah, you should know that this value in for here. So yeah, this part, yeah, our final goal can be expression ku equal to f, so that this part become k and u here. So, and then remaining part become the f, so that this is a local stiffness matrices, and then remaining part is forces. Yeah, so that this is a body force. Yeah, this is a surface nodal forces in here. So that to solve this equation, you should know that this boundary condition in here. So anyway, so those kind of way, yeah, you can obtain we have two element in here. So this is local stiffness matrices, and then after assembled into the global stiffness matrices, so that, and then yeah, so this force vector also similarly assembled, and that this part, yeah, in the previous slide I do not mention about, and here, yeah, there are some boundary condition, yeah. So x equal to second point, yeah, equal to r specific value, and then remaining part, yeah, there are, if they don't mention about it, maybe equal to 0, and then this u value is special boundary condition, yeah, maybe similar fixed boundary condition of the displacement. So that, yeah, this is r specific value, and then after then, yeah, how can we solve it? Yeah, already applied. Yeah, this part become equal to 0. That means that you can cancel out, and then this part become 1. Yeah, here. So that this is a same form of the 2 by 2 matrices. Yeah, so or same form U2 and U3 equal to the BL1, 2. Yeah, so that after the adding two part, yeah, PL, yeah, EPL plus R, and then apply taking inversion, you can obtain the solution U2 and U3. So yeah, to solve it, yeah, so that I added the A, B, E, L, and remaining R all equal to 1, so that the exact solution you can expected those kind of exponential curves, so that FEM result shows those kind of term. Yeah, this part is due to the boundary condition. We know that this is the second nodal point and this is the third nodal point, so that maybe that we obtained those kind of solutions. So yeah, this is for the introduce of the Galerkin residual method. So compared to the potential energy approach method and then direct stiffness method, yeah, I think the first time it will be very hard to understand, but after the understanding this method, yeah, you guys can expand it, dimensions or theory or other. So that I'm going to give some homework to practice this Galerkin residual method. So this is a first part. Yeah. Second, yeah, this is for the FEM truss example. Yeah, I prepared a very simple 2D truss problem. Yeah, we have a single first and second and third nodal point, and then first and third nodal point are fixed, and then I applied the external forces in the x and y direction separately, or combining forces on the second nodal point. How can you solve it? Those kinds of cases. To solve it, we should obtain the local stiffness matrices first. This matrices, this truss element is rotated 45 degrees, so that the result L over AE, and then how can you obtain that? 0.5, but collect to outside, so that this result looks like this. And then second element, please, how can you define that? This is our basics, and then this part, so the total rotation angle 135, so that cosine theta is 1 over 2 square, and the sine theta is 1 over 2 squares, so that the rotation angle, rotated transformed local stiffness matrix is looks like this. And then how can you assemble it? Let's try it in this slide. Here 1 1 1 1 1 1 1 1 minus, so we need more spaces, so 1 1 1 1 1 1 1 1 minus 1 1 minus 1 1. So that this is a first second node, this is a second and third node, so that means that plus 1 minus 1 minus 1 plus 1 and minus 1 minus 1 1 minus 1 minus 1 1 minus here remaining equal to 0, so this become 2, this become 0, this become 0, this become 2. This is assembled cases. So I prepared in here, and then looks like this. And then finally global stiffness equation, and looks like this. And then we have 3 nodal point, and each node has a 2 degree of freedom, so we have a total 6 degree of freedoms. Looks like this. And then what is the boundary condition? This is a fixed, this is a fixed, this two has a some external forces, and then that is a px, that become py. So and then maybe equal to 0, so that we have a 4 unknown, and then 4 unknown reaction will be obtained. Then we have a 2 unknown displacement value in here, so that please applying the boundary condition, so that we can obtain the reduced matrix, and looks like this. And then you guys can easily compute it to this 2 by 2 matrices, and then we obtain this equation. After the obtain, then you can put some of this value in here in previous slide. EAL P1, EAL P2, and then remaining reaction force you guys can obtain after the matrix multiplications. So we can solve this problem by your hand. However, so how can we solve the chord? I already introduced the one-dimensional truss FEM chord, so that today I'm going to introduce the 2D truss chord by MATLAB. So that first we should define the node and element and other material property or boundary conditions. So that I think that a node contains coordination information and x and y coordination, and element is a connectivity. In first element they have a second and first and second node, and then in the second element second node and third node are connected to each other. Yeah, connecting information. The element must contain connectivity information, and each element has a specific cross-section area or Young's modulus, and then you should add the material property each in element. And then boundary condition or pulses vector, you should define the pulses vectors, and that this other display. If you have a boundary condition, so then I'm going to 1 or 0 boundary condition, and then yeah, you should define the local stiffness matrix L over AE, and then cosine 제곱 sine square, yeah, cosine sine, yeah, blah 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 blah, yeah. So symmetric, so that, and then yeah, assembly, yeah, assembly method is very simple. So that after the obtain the assembled global stiffness matrix and then applying boundary condition, you can obtain the displacement solution. So that this is a process how to obtain the 2D Turss MATLAB code. So that I prepared the MATLAB code. Yeah, I made this code last year. So that yeah, in previous slide. Yeah, I think that this is a first, yeah, second, third. So that the origin, this first node is origin and x, x, and then they have a one. I forgot the exact. There are here the element length is equal to 1, so that the coordinate, yeah, 1, yeah, this is each length coordination is 1 over square 2, yeah, okay, so that I put this value in here, and then third coordination is coordination equal to 0, and then this is twice of the second node y coordination. So that boundary condition is a forces is only applied in second order point in the 1 meganewtons and each x and y directions. So and then boundary condition, yeah, first and third nodal point are fixed, so that in x direction, in y direction, and this is the x and y direction of the third, yeah, second, this is the first. So that this is a, yeah, defining system. And then yeah, also yeah, element variable, yeah, first and second node are connected to each other, and in the second element, second node and third node point connected to each other. Yeah, this is information, and the Young's modulus, and then cross-section area also added in here. So that this is the main part. Yeah, so that yeah, before we start, we should yeah, this is a computational cost. Yeah, please predefine the size of the global stiffness matrices, so that we have a 3 node point, each nodal point 2 degree of freedom. That means that we obtain the 6 by 6 global stiffness matrices, and then I put some the 0 value in first, and then yeah, how many time we should calculate the local stiffness matrices. Yeah, we have 2 elements, so that here check the number of the element. In this element we have 2 number of the element. Yeah, this proof twice time they will calculate it. Yeah, and then first try, yeah, first at the nodal element information we obtain the x coordination, and second coordination. This coordination may be, yeah, x1 y1, yeah, x2 y2, and then yeah, we have only put some the coordination information, so that yeah, so that to define the local stiffness matrices we should know that the length of the element. So that this L is a, yeah, this equation is for the distance between the 2 points, and then Young's modulus contains the element indexes, and cross-section area also contains in element variable in here. So and then next thing is what is the, yeah, we already know that those kind of solution. So that if you are familiar with this, but yeah, sometimes it's very confusing to memorize this one. So that I'm going to use our local frequency matrices is a transpose matrices, and looks like this. In here, K1 is this matrices, yeah. So that I use this K looks like this, and transpose matrices. What is a transpose matrices? Cosine, sine, minus sine, cosine, and remaining part. This is a transpose matrices, and then in previous lecture, so that we learned about how to rotate it, or use this transformation matrices. Our K local is a multiplication T transpose and K local sequence matrices and T matrices. Yeah, that will return those kind of blah blah matrices. So that, and then yeah, we finally obtain the local sequence matrices, and then we should assemble this local sequence matrix into the global sequence matrices. So that similarly, I use some technique. Yeah, this is a summation K global and then K global plus K local. In here, we have a 4x4 local sequence matrices. That means that we have a 16 element. In the previous 1D cases, we have only 4 elements. So that I write down the 4 element summation separately. However, in these cases, we need 16 lines to assemble this equation. However, to reduce the summation, so I use 4 loops, so that each 4 loop runs twice, so that total they will run both times, so that I have 4 lines, so that total 4 by 4, yeah, 6 times, so that I can use those kind of algorithm. I can easily assemble our local sequence matrix into the global sequence matrix. So anyway, yeah, this first element strongly related to the first and x and first x, so that yeah, we can check our local element is some first indexes and second indexes. Next time I will introduce more details. So yeah, so anyway, so after the learning, we obtained those kind of local sequence matrix. Looks like this. That this is a calculated value, and then yeah, this after the learning, yeah, first K global and looks like this, and then first assembled properly, and second element will be added properly. So that, and then next is a boundary condition. So that if they have some boundary condition, yeah, please remove the 0 and 0, and then changing the 1, and then force is also equal to 0. Always force vector is already defined equal to 0. So that, and then this is a reduced matrices. Yeah, all this term become equal to 1, and then yeah, take inversion K global forces, so that we obtain some solution. So that yeah, to plot this result, yeah, you should changing the shapes of the plot using the reshape method. Yeah, this vector can be changing the exact position, so that using the transpose, so that this is a x and y displacement of the first node, and this is a x and y second, and this is a third node, and then we already know that the exact node position, yeah, update means that in the previous slide, yeah, adding the displacement, so that those kind of way we can obtain the deformed geometry. So that this is a plot, so that I just plot each point and line, each point and line, but we have a initial, yeah, this is a initial undeformed cases. Yeah, this is after final or deformed the structure, so that this first and third node does not move, but the second node point slightly deformed, so that we can draw the deformed geometry by the plot method, so that it's just drawing. So after the make those kind of function, so that in the previous slide, after making the function FEM to the Turss, if you guys put some the information, and then you can obtain those kind of solutions, so that every cases 1D Turss and 2D Turss and 3D cases, after the making those kind of function, you can use freely, so that if you have those kind of variable information, so the commercial software, they have 2 or 3 main component. First component is defining geometric, and second is a solver, and the third one is a drawing plot, a post process. So that in this lecture we are going to learn about how to solve to make a solver for the FEM simulations. So that so I already told you about the 2D MATLAB code. After the write down again this 2D Turss element system, that please check this problem. This Turss system has a total 11 element and 7 node, so that it is hard to compute by your hand, so that please try to buy MATLAB code. And then I think that next time I'm going to show you how to console can do the same process, so that please compare your solution MATLAB and console. This is our next homework. So that this is the end of the summary. So that during the 2 lecture we learned about the residual method, and then we also learned about how to use the symmetric geometry. So that please do not forget today's lecture. I think that today's lecture is a very most important lecture, so that if you without understanding residual method, so I don't think you guys can do the 2-dimensional simulation plane stress and plane strain cases. So 오늘 강의를 먼저 쭉 이어서 2 파트를 조금 얘기를 해봤습니다. 첫 번째 이제 레지듀얼 메소드, 아마 이제 강의를 제가 2개로 쪼갤 것 같은데요. 레지듀얼 메소드에 대해서 쭉 공부를 해봤고요. 그 다음에 또 저희가 대칭 구조에 대해서 좀 얘기를 해봤었는데요. 대칭 구조 같은 경우에는 이제 뭐 구조가 대칭성이 보이시면 그걸 줄이시면 됩니다. 적절하게 잘 줄이시면 되고요. 보통 시험 문제는 제가 대칭성을 이용을 해야지만 풀릴 수 있는 수준이 되다 보니까 꼭 대칭성 있는 문제를 낼 수밖에 없습니다. 그래서 꼭 한번 손으로 푸는 것도 연습을 해보시고요. 근데 뭐 얘기는 했지만은 컴퓨터의 컴퓨터 퍼포먼스가 너무 좋아졌기 때문에 요새는 이렇게 대칭성을 줄여가지고 하진 않습니다. 여러분들이 시스템을 디자인할 때 특별하게 문제가 없으면은 웬만하면 이런 대칭 문제를 고려를 하지 않고 그냥 풀 시스템을 요새는 풀고 있습니다. 그래서 그래도 이제 어디 가서 이렇게 줄일 수 있다라고 기술을 알고 있으셔야지 되니까요. 좀 소개시켜 드렸고요. 그 다음에 이제 레지듀얼 메소드 조금 수학적인 내용이 좀 들어갔습니다. 제가 자세하게는 설명드리지 않았기 때문에 당연히 이해가 안 갈 겁니다. 첫 번째는. 근데 이런 방식으로 이런 스티프니스 이퀘이션이 증명이 되는구나. 증명이 된다까지만 먼저 기억을 해주시면 좋을 것 같고요. 사실 이제 레지듀얼 메소드를 조금 더 수학적으로 공부를 하면 좋긴 한데 저희가 수학적으로 그렇게 막 하려고 하는 게 목적이 아니다 보니까 여기까지만 그냥. 그래서 사실 에너지 메소드로 해도 되고요, 레지듀얼 메소드로 해도 되는데 저는 개인적으로는 레지듀얼 메소드를 조금 더 좋아하고 있습니다. 왜냐면은 여러 이제 다중 물리 현상을 풀 때 유한 요소를 갖다 제가 접목을 할 때 에너지 메소드를 매번 정의하기가 어렵습니다. 뭐 열 에너지, 유체 에너지, 뭐 고체 운동 에너지 이런 것들을 매번 에너지 형태로 정의를 해서 만드는 게 쉬울 것 같은데 심플한 시스템에 대해서는 쉽지만 복잡한 시스템에서는 이제 에너지를 서로 어떻게 핸들하는지도 좀 의견이 많이 갈립니다. 그러다 보니까 저는 이제 각각의 피직스, PDE를 갖다가 따로 푸는 거를 좀 더 선호를 하고 있고요. 그러다 보니까 여러분들에게 이런 레지듀얼 메소드를 소개시켜 드렸으니까 조금 어려워서 이번 주 한 주 동안에 배웠던 내용들이 이해가 안 가실 수도 있는데 그래도 먼저 이렇게 푸는 것까지 다까지만 기억을 해주셨으면 좋겠고요. 제가 아마 이제 이거를 조금 더 이제 2D 케이시스까지 확장을 하다 보면은 그때 이제 여러분들에게 조금씩 더 반복적으로 조금씩 하나씩 더 추가해서 알려드릴 예정이니까요. 혹시 이해가 안 됐다고 해서 왜 이렇게 어려운 거에? 라는 생각하지 마시고 그래도 조금 어려운 게 있어야죠. 사실 FEM 자체가 매트릭스 정의하고 어셈블리하고 풀면 끝인데 그 안에는 실은 더 복잡한 수학이 사실은 있습니다. 근데 그래도 여러분들에게 이게 학부 과정이다 보니까 이렇게 되는 것까지만 보여주니까 그래도 조금 이런 거 배웠구나 라는 걸 알면 나중에 여러분들이 뭔가 수치적으로 뭔가를 풀어야 될 문제가 있거나 그때 미분 방정식이 있는데 컴퓨터로 어떻게 풀어야 될지 할 때 이런 키워드를 검색해서 해보면 되겠구나를 생각을 하시고요. 사실 제가 오늘 가르쳐 드린 정도면요, 사실 1차원 변수 한 2차원 변수까지도 사실은 그냥 할 수 있습니다. 웬만하면은. 그래서 저는 그냥 할 수 있을 거라고 생각을 하는데 사실 1차원 문제들은 다 할 수 있습니다. 이제 그래서 조금 방법만 아시고 계시면은 이렇게 코드를 짜서 할 수도 있고요. 사실 매트랩이나 이런데 솔버가 잘 되어 있습니다. 이제 뭐 여러분들이 이제 실습을 하고 있는 콘솔 프로그램 같은 데에서 워낙 이제 잘 되어 있어서 그냥 값만 입력을 이제 변수값들이나 이런 바운더리 컨디션만 정확하게 입력을 해주면은 나오긴 하는데 그거는 뭐 나중에 필드에 가셔서 그냥 편안하게 이용을 하시고요. 그래도 수업이니까 이런 이론을 기반으로 갖다가 하는구나 까지만 기억을 해주셨으면 좋겠습니다. 그래서 아마 이어서 콘솔 강의에서도요, 오늘 방금 이제 했던 이런 이 문제에 대해서 조금 더 진행을 이제 콘솔로 하는 거 보여드릴 테니까요. 여러분들은 숙제로 지금 보이는 그림을 갖다가 매트랩과 콘솔로 갖다가 해서 그 노달 디스플레이스먼트랑 리액션 폴스들을 갖다가 비교를 해주시는 것을 이제 숙제로 조금 해주시면은 트러스 케이스는 이제 거의 끝난 것 같습니다. So this is the end of the today's lecture. Please, if you have any question, please send email anything you want. So 수고하셨습니다.